This is Professor Darif Seitz, binomial distribution. This video shows how to calculate various probabilities for a binomial probability distribution. The three blue cells require you to enter parameters for your particular distribution. You have to know the number of trials, n, and remember, in this kind of an experiment, each trial is independent with no effect of one another. You also record here, enter the probability of success, which is the same for each trial. However you interpret what a success is. These experiments have one of two outcomes on any given trial, either a success or a failure. And x, the random variable here, represents the number of successes in those n trials. For this sample, we have 75 successes out of 100 trials with a probability of success of 67%, of course entered as a decimal, 0.67. This section here uses Microsoft Excel formulas and functions to calculate the various probabilities that you will be interested in. The first one is the probability of exactly x successes, 75 in this case. And it uses the binomial distribution function in Microsoft Excel, which takes these three parameters and a literal false, which means it's not a cumulative. The next is the probability that the number of successes will be less than or equal to x. And that uses the same binomial distribution function with a true parameter in the fourth position, which represents a cumulative probability, not just x, but less than or equal to x. The next probability is the probability of the number of successes being strictly less than x, whatever x is up here, strictly less. And this one, there's a comment here. Let's read the comment. Being less than x for whole numbers, which is what we're dealing with here. These number of successes have to be whole numbers between 0 and n, the number of trials. You could have no successes, or you could have n successes, or anywhere in between. But to have less than x is the same as less than or equal to x minus 1. Here's an example of that. Less than 4 for whole numbers is the same as less than or equal to 3. So this formula uses this function with b1 minus 1, which is the number of successes minus 1 as the first parameter to get strictly less than x. The next is the probability of getting greater than or equal to x successes, and that's the complement of getting less than x successes. So it's 1 minus what's in cell B8. The next is the probability of strictly greater than x, which is the complement of less than or equal to x, B7. These are all the possibilities of interest that you will be having to determine probabilities for. You just need to interpret your problem, see which one of these you're looking for, and put the appropriate value of x up here in this first blue cell. This group here calculates, first of all, the probability of a failure, which is the complement of the success, so it's 1 minus the probability of the success. The next calculates the expected value of this binomial distribution. That's another very intuitive name for the mean of this distribution, and for these distributions it's n times p, and that's the formula that's used to calculate this value, 67 being the expected value with these the parameters n and p for this distribution. The variance is n times p times q, and the standard deviation is always the square root here of the variance. This last group identifies the left and right outlier boundaries for this distribution, calculating those as the mean minus 2.5 times the standard deviation, and the mean plus 2.5 times the standard deviation. This spreadsheet is very powerful because to calculate these kinds of probabilities for this distribution manually or even using a calculator are very time consuming and error prone. This will allow you to very quickly get answers that are accurate, and you can focus more on understanding the meaning of all this rather than the mechanics.